Okay, STL algorithms are the last piece of the puzzle for the STL topic in general. They're not too hard to grasp after you've done the other stuff. They are functions that execute on an iterator. And this is really important. STL algorithms only work with iterators. They don't work with containers. They don't even really understand most of the time what they're working on. So that the iterator is the abstraction point. And similarly, most containers don't understand what algorithm's working on them. And this is an excellent way to keep healthy levels of abstraction. So this is a C-style way of solving a problem. You have a nums array with numbers 1, 2, 3, 4, 5, and you want to sum over it. So you create a sum variable, you set it to be 0. Then you say, yep, we'll iterate whilst I is less than the size, sum plus equals I, and you print out the sum. Bit ugly, but it works fine. Whereas this is a slightly nicer way of iterating through it, using iterators, summing it up manually still. And then we have this way, which is the for range, summing it up manually still again. So that's what we've been doing so far. An STL algorithm might look something like this. There is a function called standard accumulate. It is an STL algorithm. Remember, STL and STD get mixed up sometimes. STD is just a namespace that a lot of stuff's in. STL is a set of libraries that exist within that namespace. And you can see that what I do with this particular function is I give it the start iterator and the end iterator for a particular container. And then in this case, because it's an accumulation or a reduction, I have to give it a starting value, like what things sum to in this case. Makes sense. Cool. I'm sure that if I went and looked that up, you would see that there's probably a fourth element to the function. I imagine that's going to be some kind of like, yeah. Yeah, like this one is them multiplying it together. Some of C++ gets really weird, but like this is an example where they're passing in like a predicate to or a function. This is I find this not very intuitive, but this is basically a function that defines it's like a lambda to multiply things. So you can control what the accumulation is because it is just again a reduction. Like for any of you who've had to do undergrad with me or similar, you know, it's like reduction is the idea of taking a list of n things and collapsing it to one value somehow. The real question is on what's the method you use to get there. So we can accumulate all those numbers together just by adding them up really easily. And the function works fine. Sum STL, 2.3, sum STL, nice and simple. So very powerful. And again, the main thing here is that accumulate, it doesn't know whether it's a vector, an array, a list, a map, or anything like that. Same interface. So you can design these algorithms totally independent of what they're working on, which makes, again, the permutation problem a lot better. This is how that sum STL or that accumulate might look. It'll be like, yep, there's an iterator called first, an iterator called last, and it will actually, inside of it, have the same implementation you have, for instance. Obviously, it's more complicated than that because it's got the little the predicate type thing, the binary operator, whatever. But that just gives you a sense. It's abstracting that away from you. Now, I have another file here that shows you some extra stuff. This has got a whole bunch of C++ thingies in it. So in this case, I've got a vector called v, 1, 2, 3, 4, 5. I can sum it up to 15 with that STL algorithm. I can also do the multiplies one that will multiply them all together. Basically, 5 factorial. Is that 120? Or is it 60? It's a different one. I don't know. Don't really care. Then you say, well, what would happen if I wanted to find the midpoint of a vector? Fact check. Thank you. I could go and get v.begin, and then I could go and get v size over 2, and then I could increment it by that amount. Now this isn't me finding 2 points in memory and picking the middle, because that would break the abstraction of the iterator. This is me finding the start, which is an abstract pointer, and then me saying, how long is it? Well, I want to just increment it by half of that, and then letting the like plus operator take me to the right point, because that'll work for a map and stuff too. It'll just move through the tree by that number of things. But where things get interesting is there are 2 other STL algorithms that are being used here. The first one is this function, standard next. What does standard next do? It is the equivalent of this. So line 17 and line 14 are identical here in terms of outcome. And what that means is that line 17, think about what it's doing. This one here, standard distance. What standard distance does is it tells you the space between 2 iterators. And then we divide it by 2. So it's really the same as saying v.size divided by 2 there. And then that'll give us a number. And then what standard next does is it takes an iterator and then it increments that iterator by some number. Now, at a glance, this might seem like pointless abstractions, based on your face in particular. You're like, what the hell? But again, these are quite simple examples too, you know, where we're not really doing anything too crazy. But if we went and had a look at these for a second, we've got standard next and we've got standard distance. We can have a look. You'll also notice that iterators are objects, containers are objects, but quite often these algorithms are just functions. Just kind of one key difference here. Returns the nth successor of the iterator. Sure. Standard distance. Return the number of hops from first to last. Sure. I think where this example might feel a bit silly to you is standard distance, probably you wouldn't use it too often to figure out the distance between the start and the end. You might use it to figure out the difference between the start and a particular element you're searching for, or an element you're searching for in the end, or 2 elements you're searching for, you know? Because the start and the end, you have the size. So you don't really need it. But this is like a way of saying I found 2 iterators that describe 2 parts of this structure. How many steps are there between them? Maybe you could use that to figure out, you know, if you delete something, how many shifts might have to happen. Again, lots of different scenarios here. And then we could accumulate here between the start and the midpoint and 0, like we've seen before, which is pretty easy too.
What would that actually represent in the map? Would that just be how it's randomly ordered?
What would what represent in a map? Sorry. So if you have like a red-black tree, right, and you iterate through it, they refer to it in the documentation as hops. You're going to go hop, 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 hop. The midpoint would be like the mid-hop of it all. So if you've got, say, like 14 jumps to do, it's like the 7th jump you do would be the midpoint. Because iterators still always rely on the idea of linearizing any kind of structure. Whether it's a linked list or a vector or a map, it still has to be linearized. We just find vectors really easy to think about because they're inherently just contiguous memory. So they're already kind of linearized for us with nice memory addresses. But with, say, a DQ or a list, a doubly linked list or a singly linked list, they're probably going to be stored wherever, you know, they get mallocked in memory. Yeah. And then find. This one's really fun and interesting. So what find does is find takes in a value that you're looking for, and it takes in 2 iterators, and it looks for it between those 2 points. This is how you might delete something. So if you know, we kind of talked about before, why can't you just delete from an array or vector, is if you're like, you know what, I want to get rid of that 4 in the vector. You could just say, well, I'm going to go find the 4, and then I'm just going to call nums.erase iterator. That's how you would delete that 4. You would find it and then delete it if you know it's there. Even if you had a function where you said delete a 4, because as a vector, the vector itself would still have to look for the 4, you know? So it's not really unperformant in the sense of you've got to search it up generally here too. All right. I'm just refreshing myself. My brain didn't immediately trigger this slide. So what we've got here is we've got a vector and a linked list, a doubly linked list. And we are calling standard lower bound on both of these. Standard lower bound returns the first iterator where a condition is true. And you can see in these cases here, you have that 5 that we're searching for. I'll make this bigger up on the screen. So, what is it? Lambda. What was it called? Bound, probably. Yeah, so here it's like, okay, well, I have a vector. There's all that. I have a linked list. There's all of that. I'm looking for the iterator to the first element that is greater or equal to the argument. So it'll basically give me an iterator to that 5 in the vector case and an iterator to that 5 in the linked list case. Now, here it is saying that the number of comparisons on a vector is log n, and the number of comparisons for binary search on the linked list is n log n. The two implementations are completely different. I think this gets into iterated types, which I come to at the end. Let me just check. Yeah, okay, we come to that at the end. So let me loop back to that one for you. Actually, screw it, we'll jump to it. Weirdly ordered. With iterators, every iterator has its own category. And this is generally based on the container. What I mean by that is that, see here how there is a, it's really quite bright on that screen. See here how we have a random access iterator. That's what a vector's iterator is. Random access means we can just like grab any point in it that we want. You can increment by a huge amount, decrement by a huge amount, whatever. You can basically do anything with that iterator. Whereas if you think about a linked list, and just to be clear, what I mean by that is that with a vector, you, for instance, can say here, you know, auto iter equals nums.begin plus 10, and it will just jump 10 spots. You know, but you can't do that with a linked list, really. Like you could, but like they don't allow you to because you can't actually jump 10 spots. You can't randomly access 10 spots in the future. You would have to maybe do like 10 specific increments, like .next, 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 .next. So different structures have different kind of levels of capability. So the iterator you get from a vector is actually really powerful, whereas the iterator you get from a linked list is less powerful. It's probably a bidirectional iterator. And for a singly linked list, or a forward list in C++, it is a forward iterator, not a bidirectional one, which means you can't decrement it. Because a singly linked list can't go backwards, right? Like if you get an iterator to an element in a linked list, a normal one, you can't go prev, you have to go next. But a doubly one can go in both directions. So different iterators will fall into different one of these buckets. Most of the ones you'll see will be like bidirectional or random access, because vectors are random access iterators. Where this comes into play, is there are some STL algorithms that will not work on certain iterators. Good example is binary search. I don't think they have it. But like, you can't binary search on a linked list, right? Because you can't just randomly jump into things. And what that means, and what this slide's getting at here, as far as I remember it, is that it's saying that I'm pretty sure, I have to double check this for you, but I'm pretty sure that when you have an STL algorithm like find, it will decide what algorithm it's going to use based on the type of iterator you give it. So if it sees a vector iterator, which is like tagged with a certain type of like iterator power, it'll be like, oh, you're random access, I can just like binary search you. Whereas if it's like a linked list, it's like, I can't do that. I don't really know why it's n log n to search a linked list. Yeah, but wouldn't it just be n? Sorry? Yeah, but like, I don't, because with a linked list, like, you just look through it. I know sorting is like log. I mean, searching is nearly never longer than n, because you just look through everything.
I mean, I think the example is trying to say that you should never binary search on linked list because it's slower than linear search.
Oh, yeah, for sure. Yeah, that makes sense. And again, I'll double check about that fact. I'm just making a couple of assumptions there. But the point is that, like, even though we have this nice world where we're like, yeah, there's all these containers and all these algorithms and they can work on each other, there are still some subtleties where you can't actually, like, I'm not sure if that's the case with standard next, because standard next iterated a bunch of points. Let me see if it, like, says anything about random. There you go. So this is a great example. What it's saying here is standard next will work on any iterator. Well, nearly any iterator. It has to be at least a forward iterator, I'm sure. But I mean, every iterator can be incremented, basically. Yeah, like every iterator has a plus plus operator. Makes sense. You've got to iterate through something. But if you look at standard next, what it's saying here is that the complexity of it is linear, because it just hops steps. So if you have an iterator and you say, I've got to go 100 steps through a linked list, it just goes, all right, we got to move 100 steps. So it becomes a linear, like, you know, ON operation. However, it makes a note here and says, however, if the compiler notices that the iterator is of type random access, like a vectors one, it will call a separate function under the hood that will just do a memory jump, that many spots. Because the iterator has that capability to jump a certain number of spots. So the algorithm just says to the iterator, hey, can you jump X spots? So when we talked before too about why do we have all these like functions that seem really dumb, like next, like why don't we just increment the iterator? The reason is because now we have a really nice abstraction where whether we're working on a linked list or a map or a vector, we can just ask it to move a number of spots and it will be able to figure out what's the fastest way to do that. It'll notice what type of iterator it is and it'll say, yep, okay, you're that type iterator, we can go real quick. Otherwise it'll look at this one and say we can't do that. There are some notes I have here where I've got iterator categories. And what we say here is that some containers will themselves potentially have extra operations in them. Like you'll notice that I think we gave the example was like, what was the good example? It was it the map? Map? Was it again? Container map. So with the map, you'll notice that there was a find function here. And the find function for a map is logarithmic. So it's O log n. And you'll see that sometimes containers will have functions in it like find or sort or something when they're not able to necessarily provide an iterator abstraction that can never be as efficient as something that understands it, right? Because the container obviously breaks abstraction. It knows how it works internally. So it can track some stuff. So you will see some examples of those kinds of algorithms like that. Like I'm pretty sure there's probably like an erase, like a stand. I don't know. I'm just making a guess now. But okay, cool. A few more things then. Output sequence. Yeah, this one is basically a what is going on here? So what this one is doing is there's an STL algorithm called transform, standard transform. It takes a begin to a container, an end to a container. I shouldn't say begin and end because it takes a first and a last because they don't have to be the whole container. They can be a subset of it. It takes a first and a last, and then what it does is it takes an output, basically the begin of another container, and it kind of writes to it. It's basically a map function. I know, again, a bunch of you did 1531 with me at one point, and we talk about like JavaScript map functions, where you take n items and you turn it into another n items. It's the same principle here, because we're taking one container, this one, hello world s, and we are simply outputting it to a second container. You don't need the dot end here, because we already know how much to output, because we've specified it here. You know, like we know what the distance is between start, first, and last, and because we know what the distance is between first and last, we just output that many elements to the second container too. And this here is a mapper function. It's like your classic Lambda, where it just takes, like, It's just it's a literal predicate. It takes in a character each time. This here has to be compatible with the type of the underlying container and stuff. You could spend some time with that code, but it's just another example of how you can use good abstractions in C++. And there's another one called back inserter. Look, there's some C++ code that some of the really smart people have showed me, and it looks like another language to me. There's characters in it I've never seen before. So when you look at this and you're like, this is starting to really seem confusing, my comment would be don't stress, because most people day to day wouldn't write code this refined, you know? Because what this person is doing here is, in this previous example, you can see that I'm not even 100% sure.
It's creating a new word, right? Just capitalized. The word's capitalized.
Well, so 2up is what capitalizes it. It's the back inserter part.
So it's back inserting into upper, like making a new.
Oh, that's adding it to the end. Yeah, sorry. Came back to me all of a sudden. So, like, the back inserter is done in place of, because like what a back inserter does is you give it a container, and it basically returns you an iterator to the end of that container that you're ready to give someone to be able to insert things into. So if we look at this again, JS Paint, you imagine you have like this string here with all these elements in it. Well, here's the part. You know that there's 2 iterators you can get from that. The first one is like string.begin, but you don't want that. And string.end, that doesn't work either. String.end is not something usable. You want a kind of way to say, hey, can you get me an iterator to like actually here? You know, like actually right at the end somehow, so that I can actually insert more stuff to the end. So when you wrap it in this algorithm, you know, back inserter, the back inserter will take that container and it will return an iterator to the end of to the back of it, ready for insertion. That's why it's called back inserter. Give something to the back, ready for insertion, and then it will insert it according to 2upper. Now again, this is very refined code. I would never just be writing code being like, I'm just going to transform the beginning and the end, and I'll just back insert this. That's very thoughtful code. So don't be overwhelmed by it.
So the size of S would change?
Yes, the size of S would change as you add more elements to the end. Last thing for today, Lambda functions. These come up in the tutorials a little bit. Thankfully, Lambdas are becoming more prominent. 10 years ago when this was added, or part of the course, I think they weren't super prominent, but now people are learning lots of things like Python and JavaScript again, which have Lambdas in it. So you should be relatively familiar with it. Let me just wrap that. And the Lambda part to extract, it's this part here. Right, I'll just write it like this for a second. Lambda. And then this is the lambda down here. It looks like this. It's basically a shorthand function. And what it has, it's very straightforward when you break it down. This is the function here, right? It's a function that takes in a reference to a character. And this is the body of the function. And it just returns to you, well, in this case, it doesn't return anything. It just changes something. You give it a reference to a value, and it takes that and it casts it to an uppercase. So this just makes everything uppercase. This function takes in a character, makes it an uppercase. This little thing here is what we call the capture. Because remember, when you create a function, everything inside that, all the elements in that function, it kind of ignores the outside world largely, right? Like functions tend to operate in isolation. This little capture is where you can go and put variables and stuff if you want them to be in scope inside that function. I don't have a great example in this one. I think we might go into it. We kind of talk about it a little bit there. There's some examples in the tutes and stuff. But
What about just some? Well, not exactly there, but generally.
yeah, I guess it's like if I had int I equals 1, and then inside this function I was like, because you might rewrite this like this, say, right? If I was like, yep, standard cout I, like this, it would throw an error, and it's like, I don't know what I is. It's not in scope. But if I was to go and put it up here like that, I believe that's how you write it. Now it's in scope. So it's just a way of like, if you're like, there's values outside of this function that I need it to have, you can kind of shove them in, let it access it, or I think it's like that.
Why is that a reference? Is it just
I don't think that's I'd need to double check the syntax. I think I'm tripping up on it. C++ Lambda capture. Yeah, I don't think it's what I've done. Example. What the hell is that?
I think you can do it either way.
Oh, X, yeah, sorry. Just I. Yes, that's how they can pass it in if you want to. Here's the thing about lambdas. They're shorthands. They're not like a feature, just like any lambda or equivalent. Like, you can program without them. They're just shorthand ways to write functions and pass them in. Typically, the way it works is that if you've written a function that you're passing into another function, and you're only ever passing it into another function once, then you make it a lambda, because it's like easier to read. This is the structure we talked about before. But just having a look at this about the captures, what was that one called? Oh, there is no sample code for it. So in this case, we've got a main function, a vector with 3 items in it. Then we call add n with that vector and 3 things. And here, the add n function takes in a reference to that vector, should probably be a const reference, and a number, and then it calls the STL algorithm for each, gives it the whole bookend iterators for the vector, and then it calls on this function. This is someone trying to write a function that takes a vector and adds some number n to every element in the vector. So you can see what it does is for each element in that whole thing, it applies this lambda function. And that lambda function takes in each value of the vector and increments it by n. But because n is not part of this function and it's not passed in as parameters, because the parameters are always whatever the underlying container is made up of, you need to pass that in through the capture there. It's a little weird. I wouldn't stress too much about it. It's towards the end of the lecture, so I don't really want to run over today after the longer lectures last week. So I'll just kind of say, play around with that, go write some code for it. You can always ask me questions about it next time. I did want to answer someone's question on the chat, and then I wanted to show you a real quick 1-minute hilarious piece of code that I always like to show in C courses, and then you get to go home. Sulux on the chat has said something about, is that a separate, can iterator categories be many? I think they're mutually exclusive, because most of them are like more powerful versions than each other. I know that isn't strictly the case always, but I imagine that is maybe the thing. There was a question, what are input and output iterators? Input, output iterators generally most common with streams. So what I mean by that is like you can get an output iterator for standard out. You can't ever compare 2 iterators of standard out. It doesn't make sense. You can't get one iterator to standard out and compare it to another. You can't really do much with it. You can only write to standard out and increment it. But we don't really do much with them. But think of them as like input and output. Great.